Great. So I'm going to tell you about a way to compute a low-rank Tucker approximation of a tensor, even if you can only afford to store as much something much smaller than the size of the tensor. So if you can't afford to put the entire tensor into your memory on your computer, you can still compute a low-rank approximation to it. Great. So I'm going to tell you about a bunch of different setups where you might be interested in doing this. This is joint work with a bunch of people. So with Joel Trop at Caltech, Yiming Sun, who was my PhD student at Cornell, he's now at Amazon, and Yang Guo and Charlene Luo, who are both undergraduates at Cornell and have now gone on to great things. Okay. Great. Okay, so first, let me tell you about sort of setups where you might be interested in this kind of problem. So let's imagine that you're generating slices of a tensor, okay, and you're going to see slice after slice of the tensor. Maybe you're computing a simulation, right? You're evolving some kind of physical system forward in time, and at each time you see one time slice of that physical system. Okay, so you're going to record each of these time slices. You're going to store them in some big database. So each of these time slices I'm representing as H sub t. So H1 is the first time slice, H2 is the second time slice. And my tensor is going to be a collection of each of these time slices. Okay, so one dimension of the tensor is time. Maybe the other dimensions are, spatial coordinates. Or maybe species of different chemical species in a chemical simulation, something like this. Okay, so I'm going to collect each of these slices, store them in my database, and then eventually want to analyze the data. And here's where I run into problems, because the total size of my combustion simulation is large, and sending all that data to my computer takes a really long time. Moreover, storing it on my computer takes a really long time. Okay, so I've marked in red these things that I really shouldn't be doing. I should not be sending the whole tensor to my computer, and I should not be storing it on my computer. I don't have enough space for that. Okay, but I'd still like to be able to analyze this tensor, and understand something about it. Maybe a low-rank decomposition. Okay, second scenario. Let's imagine I've got distributed data. Okay, now so now I'm in a setting where I've got a bunch of different toasters, each generating slices of my tensor. Again, I'm going to collect them all onto a database, and I'd like to analyze them on my computer. I'm still in trouble because I don't want to send that data to my computer or store it on my computer. Okay. Third scenario is I never collect I don't want to collect all of the data in the same place. Instead, what's going on is I've got a smart toaster, and every day it toasts, it makes me some slice, and I've got the data about the slice today, and this toaster has enough memory that it can store data about the slice today, but it can't store all the information about each slice over time. Okay, so I'd like to understand something about the sequences of slices that I'm seeing of my tensor, and I can't do it because I can't store that amount of information. Okay, so here's the computational model that I'm going to be working with. It's called the turnstile model, where the entire tensor that I'm seeing is a sum of sometimes we call them innovations. They're smaller, simpler tensors that are called H1 through HT. So at every time I'm presented with a new simple tensor HT. So you might imagine that it's a slice of a tensor. It could be otherwise structured. Maybe it's a low rank, maybe rank 1 tensor. And the requirement that I'm laboring under is that I have to discard this innovation after it's processed. All I'm allowed to remember is some much lower dimensional, sort of smaller amount of information about these innovations that I've seen. Okay, so the goal is that without storing the entire tensor, I want to approximate the tensor after having seen all the updates, and I want to do that with guaranteed accuracy. When might I want to do this? So I've already told you about this application in scientific simulation. Maybe I want to be able to, compress or store or otherwise understand sort of important aspects of the data that I've seen from this simulation without storing all of the data.
So Joe Landsberg asked, what is the size of XT versus T?
What is the size of
X sub T versus capital T?
So here, actually, each of these tensors is the same size, but these innovations are generally structured. So for example, they might be 0 except on a single slice, right? So if I store them in, if I note which slice is non-zero, then they're going to be much smaller. Right? generally, like they have sort of one fewer mode than the complete tensor. Okay. I might be doing this in the context of sensor measurements, where each time I get another measurement from a sensor, and that measurement is a has itself several dimensions. I might be doing this in the setting of low memory optimization. So this is actually the application that originally sparked our interest in this topic. Is there several algorithms for optimization where it's sort of a classical scheme for optimization. Every time you see an additive update to your decision variable, and maybe it may be easy to store that additive to compute that additive update, and yet storing the sum of all of those updates can get very expensive. Okay, so we were interested in whether we could say something about the sum of all these additive updates without having to store the sum. Okay, so let's talk about the kind of thing that we're going to store. And what we're going to store is a linear sketch of our tensor. Okay, so it's going to be some linear function of the entire tensor, and it's going to map the entire tensor down onto a lower dimensional space. Okay, so I'm going to represent that with the operator L. And the nice thing about linearity is that this linear sketch of my complete tensor X is equal to the sum of the linear sketches of each innovation. Okay, so if the output of that linear sketch is something that I'm willing to store, then I can compute the linear sketch on each innovation. Then it's very easy for me to update my sketch of the whole tensor by computing my sketch of the innovation that I see at each time and adding that to the sum of the sketches of the previous innovations. Okay.
So Joe Landsberg has a question. You want to take it?
What's that?
Yes. Joe Landsberg has a question.
Oh, great. Yes.
Yeah. So no, I guess I wasn't clear about my question. So say each of these HJs is a matrix, and I want to know the size of the matrix versus the number capital T of matrices. Are they of the same order, or are the matrices enormous and the number of them is small, or what? Or you're talking about something so versatile it'll work?
I'm talking about something pretty versatile. So, in fact, each of these. So imagine that. So I'm talking about it like they're slices, but the framework is pretty generic. So the way that I'm treating it mathematically is like each of the H's has the same size as the tensor X. That's why I'm allowed to add them up. But what's going on is that the reason that I might be interested in this is if each of the H's is simpler than the overall tensor X. Okay, so you shouldn't imagine, although they're each the same size, you shouldn't imagine that they're all dense tensors. X might be a dense tensor, whereas H, maybe it has, it only has one non-zero slice. And I'm not going to tell you which particular slice, but a common application is that there's sort of one distinguished dimension, and each of these H's is non-zero only along one slice along that distinguished dimension, which is maybe time.
I see. Okay, thank you.
Okay,
but that's a special case. So when you write plus, you actually mean plus. So the cartoon would be that H only is zero except for a specific value of time, but it could be anything else with some lower complexity.
That's right. Yeah. So in the optimization application, actually each of these H's might be a rank 1 tensor.
Okay. All right.
Right. So in that case, actually they're dense, but they have a simple representation that might make it easy to compute a sketch.
Okay. All right. Thanks.
Great. Okay. So the important thing is that the sketch is much smaller than the input tensor, and we're going to use randomness in the sketch so that we can guarantee that our algorithm is going to work well for any arbitrary input. Okay. So these are the ideas. Okay. And essentially, actually, it was proved by in a paper by David Woodruff and co-authors that this is essentially the only way to handle turnstile data if you want to sort of remember only a very small amount of information about your overall object, and you can only sort of handle one of these innovations at a time, and they can have positive and negative entries. Then you need to use a linear sketch. Okay, so what are some examples of linear sketches? One is contracting your tensor with a matrix along some mode. Okay. Another is contracting your, is doing that along sort of each mode. Okay, so for each mode, contracting your tensor with a different matrix, okay, and collecting the output of all of this. So this is actually maybe the most important idea, is that you can have a linear sketch, right? So you know, how would you, I mean, so each of these sketches is linear. So the concatenation of each of these sketches is linear. Okay. So I'm allowed to sketch my tensor by contracting it with a different matrix along each mode, but I can compute all of those at the same time, right? It's still linear. And so in particular, if I want to compute a sketch of X, and X is a sum of H's, I can compute the sketch for each of the H's and then add up the sketches. Okay. Great. Okay. So the main idea of this talk is that computing a sketch like that suffices to allow you to compute a Tucker approximation of your tensor. What we're going to do is we're going to compute a randomized linear sketch of our tensor along the lines of what I just showed you on the last slide. And we're going to use that to recover a low-rank Tucker approximation of our tensor from the sketch. Okay. There's also a way to improve the approximation by revisiting your data once. So if you're willing to sort of generate the entire tensor twice, you can do better. I'll show you that too. Okay, so here is, you know, how would that help in these sort of computational settings I outlined before, right? So you're, you know, you're seeing one slice of the tensor at each time. You put all those into the database, then you can compute the sketch and transmit only the sketch to your computer and analyze just the sketch. Okay, so that way you're only transmitting a small amount of data and you're only storing a small amount of data on your computer. Second setting, this distributed setting, right? So you don't need to collect all of the information into one place. You never need to store the entirety of X. Instead, you can imagine computing the sketch of each innovation and adding up the sketch of each innovation, okay? This, again, has the benefit of reduced communication. The sketch of the data fits on your laptop, and sorry, this is just tongue-in-cheek, but you could imagine a privacy angle where you can say that, look, you're not transmitting any personally identifiable toast information. Okay, that's just a joke, so don't take it too seriously. Great. The third setting is in the streaming data setting. Okay, and this is kind of cool. So here what we see is, again, I'm just using linearity. Okay, so it's super simple math. The sketch of the sum of the innovations observed up to time t is equal to the sketch of the sum of the innovations observed up to time up to time t minus 1, plus the sketch of the innovation at time t. Okay, so I don't need to, you know, okay, so at each time I just need to take what I previously stored and add to it the sketch of the innovation I've observed at this time. Okay, so this allows me to work on streaming data, right? I can compute a sketch from streaming data. Great. Okay, so now let me tell you how these algorithms work. Let's imagine my tensor to compress. Again, I'm going to call it X. It's going to have n modes. So I'm not specializing to order 3 tensors or anything like that. I'm sometimes going to assume that each of the modes has the same dimension, just for simplicity of notation, but there's no real restriction. These don't have to be square tensors. Okay. I'm going to use bracket n for indexing. So bracket n is going to represent the integers 1 up through n. And I'm going to use this notation is pretty important. I sub minus n is the product of the dimensions of all of the modes except for the nth one. Okay, so that's actually going to be the dimension of the of one side of the nth unfolding. Okay, the tensor operations that I'm going to need to use are the mode n product. Okay, so that's contracting my tensor with a matrix along the nth mode. And I'm going to use the unfolding of my tensor along the nth mode. Okay, so what that's going to do is I'm going to take, take my tensor, look at the fibers that run along the nth mode, and I'm going to collect those as rows, as columns of a matrix. So the result of an unfolding is going to be a very, 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 very fat matrix. The number of rows is going to be the same as the dimension along the nth mode, and the number of columns is going to be the total number of fibers that run along that nth mode. Great. Okay, so the object that I'm trying to compute. So the goal of this talk is to compute a Tucker factorization from a sketch, an approximate Tucker factorization. So what is a rank R Tucker factorization of a tensor? It's a different. So this is a different notion of rank than what you heard, for example, in Talil's talk. This is sometimes called the a multilinear rank. Okay, so what is it? It takes a smaller tensor, G, okay, which has dimension Rn along the nth mode, and that's called the core tensor, and it sort of projects up into the entire, like the big space of the tensor, using these factor matrices Un for each mode n. Okay, so you can think about it as it's actually a sum of rank 1 tensors, and it's a sum over each entry in this core tensor. Okay, again, I'm sometimes going to assume that we've got the same dimension along each mode of the core tensor. Okay, so the Tucker factorization is useful for compression. When the number of modes is small, you can store many fewer numbers to compute you can store the same number of numbers that you would use in a CP approximation to compute a rank R approximation of the tensor. Using the Tucker approximation, you can compute a rank R cubed approximation. Okay, so if you want to get up to higher ranks and store the same number of numbers, Tucker is your friend. At least when you've got a small number of modes. When you have a large number of modes, there's an extra term that I'm hiding here, which is R to the N. So if R to the N is small compared to the dimension of each mode I, then the Tucker factorization will be your friend if you're looking for good compression. Okay. So how do I compute the Tucker decomposition? There's a classical algorithm that's it goes all the way back to Tucker in 1966, but was really popularized by Lehman de Lathauer and co-authors around 2000, which is the higher order singular value decomposition. So how does this work? For each unfolding of the tensor, I'm going to compute the top Rn left singular vectors of that unfolding. I'm going to contract these again with my original tensor X to form the core of my tensor. Okay, the result is a Tucker approximation. So I get the factor matrices from the first step, and I get the core from the second step. The most important thing for our purposes to note about this is that you really need to look at X twice here. Once to compute the factor matrices, and again to compute the core. Okay. And you really need to look at it twice. You can't do both at the same time because you need to have already computed the UNs before you revisit X to compute the core. Okay. So that leads to a pretty straightforward idea, which is a two-pass higher order singular value decomposition. Okay. So the first step is to use randomized linear algebra to compute the factors. What I'm going to use is that I need to find the span of the fibers of X along the nth mode, right? Here's the way that I'm going to do that is using randomized linear algebra. So I'm going to take a random matrix omega. I'm going to compute the product of the nth unfolding of X with omega. And I'm going to use the fact that as long as the rank of omega is large enough compared to the rank of the unfolding, then the range of this unfolding along right in the range of its columns is the same as the range of the columns of the unfolding times omega. So if omega, if I choose it to be the right shape, I can get a good approximation, but I'm computing the range on a much smaller matrix. Okay, so the algorithm is compute a sketch. Right? And the sketch is going to exactly be this, the unfolding contracted with omega. And then I'm going to use a QR factorization on X and omega in order to compute the range of its columns. Okay, and that's a good approximation for the range of the nth unfolding. Okay. For the core computation, well, that's already linear in X. So if I'm willing to see X twice, I can compute the factor matrices UN using the sketch, and then I can look at X again to compute the core matrix, the core tensor. Okay, I'm running a little bit slow, so I'm going to there's an alternative way to go about these things that uses the higher order orthogonal iteration. There was previous work on one-pass algorithm for computing a Tucker decomposition that used ideas from the higher order orthogonal iteration. They weren't able to prove guarantees on their one-pass approximation, but it's still a sort of a clever and interesting idea. Okay. Okay, so let me go a little bit deeper into how we use these randomized sketches. Okay, so here's the idea, right? The idea is that if you pick a random matrix omega, it will not be orthogonal to the range of interest with high probability. Okay, and so with high probability, we're going to get that the range of the nth unfolding is equal to the range of xn times omega, as long as omega is large enough. Okay, so we're going to call in a matrix that a random matrix omega that has this property, a dimension reduction map. Okay, a dimension reduction map is going to approximately preserve the range of its argument. So examples of dimension reduction maps are probably the most common one is a random Gaussian matrix, has this property. You can also make the matrix omega sparse. You might make it structured. And the most important one for our purposes is going to be the tensor random projection, which we developed again with the same co-authors. Okay, so I'm going to tell you why that is in a moment. Okay. So here's the sketch that we're going to make in order to compute a Tucker approximation. The factor sketch is going to look like this, right? I'm going to compute a different random matrix omega for each mode, and I'm going to contract my tensor with that random matrix along that mode to produce this sketch Vn along each mode. Okay. I'm also going to sketch the core. The way I'm going to sketch the core is I'm going to pick a random matrix for each mode, and I'm going to contract my tensor with each of those random matrices at the same time. Okay, so this is right. So each of these results is a little matrix, and this thing is a little tensor. Okay, the rule of thumb, how big the quality of your approximation is going to depend on the numbers kn and sn. Okay, so how big should you pick them? Well, k you should pick as big as you can afford, and s you should pick to be twice k. It's going to give you guaranteed good reconstructions. Okay, so I'm going to define this collection, right? This core sketch and these collection of these factor matrix sketches as to be the sketch of my tensor with respect to these dimension reduction maps. Great. So here's one major problem with this approach is that the factor sketch dimension reduction maps are actually really, really big. Okay. In fact, the number of numbers in them is not much less than the original size of my tensor. So if I can't afford to store my tensor, I cannot afford to store my dimension reduction maps. Okay. So what should I do instead? There are two different ideas. One is, well, don't bother storing them. Just use a pseudo-random number generator to generate these on the fly as needed. Okay. The other idea is you can use a structured dimension reduction map. Okay, and the one that we used, which we developed in a paper, it's also very closely related to some work by Mark Rudelson on random row products of matrices. It generates a large matrix by basically taking a sort of vec of a cat3 row product of smaller dimension reduction maps, and you can prove that construction still satisfies all the properties that you need from your dimension reduction map. Okay. The other nice thing about it is it's actually right. It is itself a kind of a Tucker factorization object, and so it plays really nicely with the fact that we're taking randomized sketches of matricizations of tensors. So it makes it actually easier to compute. Okay. So let's talk about how we recover the factor matrices from these sketches. Okay, essentially what we said is that the range of the nth unfolding of our tensor is the same as the range of this factor sketch, Vn. Okay, so all we have to do is compute its range. What we do, the way that we do that is we use the QR decomposition. Okay, you can also use a truncated QR decomposition in order to truncate the rank of your Tucker approximation to whatever you'd like. Okay, so this already gives a two-pass algorithm, okay, which is kind of the same as what I told you before. Great, so I'm not going to say too much about it, right? But it accesses the matrix twice, once to form the sketch up here, and then once to recover the core, okay? Because after I've formed the sketch, recovered the ranges of each factor matrix, I have to contract those with X to form my core. Okay, so how do I get away from this? How do I get to a one-pass approximation? And the main idea is I have to figure out how I can approximate the core using just a sketch. Okay, so here is the main idea, right? I have this core sketch, right, which was a compression of X using random projections of phi. Okay, so what I'm going to do is I'm going to notice that X should be approximately equal to X sort of projected onto the space that's spanned by these factor matrix approximations along each mode. Okay, I'm going to collect terms and observe that this core compression, which is what I want to approximate, this W, okay, sort of is of this form, okay? And so, okay, so now I'm going to take both sides of this, approximate equation, and I'm going to compress both of them using these random projections phi, okay? When I do this, I can see that this object on the left side is the sketch, right? That's something I've computed and stored, okay? And the object on the right side is W, that's what I want to approximate, times a bunch, right, or compressed onto the range of each of these small matrices. Okay, the key property of the way that I've chosen my sketches is that each of these little matrices is invertible, okay, with high probability. So I'm going to invert them, and in doing so, I'm able to solve for W, right, which is the thing I want to know, the compression of the true tensor X onto the factor matrices Q. In terms of what I do know, which is the sketch H. Great. Okay, so that gives me the one-pass algorithm. Okay, so I compute the sketch, I use that to compute the factor matrices, and then I use the core sketch along with this idea to recover the core. Okay, that gives me a Tucker approximation. Okay, now that I've accessed X only once to sketch. Great. I can also truncate this approximation by just truncating the core to rank R. Okay, so I might sketch using a large approximation, and then later I can decide, oh, actually, this tensor can be well approximated with a rank that's even, a Tucker rank that's even smaller, multilinear rank that's even smaller. Great. So to tell you about how well this works, I need to talk about the tail energy in the unfolding along each dimension. Okay, so that's the sum of the energy and the singular values that I've left out. Okay. Okay. If you use this sort of Tucker sketch with the recommended parameters, right? So if you use if you're going for a rank R approximation and you use parameters for the factor matrix sketches that are one larger than the rank you're going for, and for the core matrix that are twice as large as that, then the Tucker approximation that you get is no worse than 4 times the sum of the Taylor energies along each mode. Okay, so 2 things to note about this bound. So if the tensor you were sketching really is rank R, then the sum of these tail terms is actually 0. We actually get exactly the true Tucker approximation, the true Tucker decomposition. Okay. The second thing to note is that you can't, just by sort of resort to facts that we know about matrices, you can't possibly do better, right? There is no rank R Tucker decomposition that approximates my tensor X better than the tail energy along one mode. Okay, so this is within a factor of 4n times the best possible approximation. Okay, so that means that this approximation is actually it's called quasi-optimal. Okay, it's within a constant factor of the best possible approximation.
So just to mention, you're essentially out of time. So
yes, I am essentially out of time. So that's really the last thing I wanted to say.
Okay.
If you use different dimension reduction maps, essentially they all perform the same. So you can just go with the cheapest one, which is quite cheap, which is the sparse tensor random projection. And the result basically gives you sensible reconstructions at practical compression levels. So it's actually a practical algorithm. It's not, despite the organization of my talk, it's not just theoretical. Okay, so let me show you some pictures. If this is your one slice of your combustion simulation, this is what it looks like. If you reconstruct with the higher order orthogonal iteration, which is about as well as you can do, this is what the reconstruction looks like. This is the reconstruction you get using our 2-pass approximation, and here's what you get using 1-pass. So you can see it's a little bit blurrier, but barely. Okay, so it's actually doing quite well and a lot cheaper. Great. So let me end there. The streaming Tucker approximation compresses the tensor without storing it. This makes it useful for streaming data, distributed data, or anytime you want to do low memory compute. Okay, the key ideas are that you can form a linear sketch of the tensor and recover from that sketch, and that the random projection of a tensor preserves the dominant information along each mode. Thank you.
Perfect timing. Thanks a lot.